there's a change of momentum. When there's a change of momentum, what do you have to apply to make that happen? A force. Of that force, there are more than one component. Is underneath. There are forces due to pressure, there's forces due to anchor. So when you account for all of that, the anchoring force is one of the pieces that hold this nozzle stationary.
And so the shape of the nozzle won't affect the anchoring force?
You tell me.
No?
You tell me. So I draw a control volume, right? And in all the calculations we did for this one as well as that one, does this matter what happened in the detail inside? No. What happened mostly is at the interface. So I'm blind. This is a back box approach. I'm blind to the exact geometry of this device. All I care is what happened at the interface. It's very nice. It's called control volume. It's back of envelope, 5-10 minutes, maybe half an hour calculation. Get you an answer good enough to do engineering estimate. Get it? So the forces you mentioned is if you hold on to a fire hose where the flow accelerated from the nozzle, as the fireman or woman, what do you have to do? You grab onto the nozzle or you're going to spring all around. So that forces is due to the acceleration of the fluid. Yes?
So what direction would the anchoring force be in that diagram?
So in this diagram, I'm trying to be very careful how I answer it. From an engineering intuition, the flow accelerated, you would intuitively think the anchoring force is something that I have to hold on to the nozzle, grab it so it doesn't go towards the door. All right? But it's not that simple, because there are problems in 2D which you have no idea which direction is this force. And I'm going to show you now, hopefully once and for all, that it's not critical that you have to have that engineering intuition. You can assume it in any direction you want. At the end, the answer will take care of itself. So I'm going to show you that right now. So that hopefully once and for all, you're convinced that you can assume the anchoring force in any direction you choose to is inconsequential. Right? Fair enough? You see where I'm going here with this, repeating the problem, which you have done. I'm just making sure it's clear. Okay, so from my intuition, just like I did before, I'm going to say the force from anchoring is pointing to the left. I'm going, just like I did with many cases, convention is plus x pointing to the right. I hope this is pretty straightforward. What pressure you would prefer to use for this control volume? Let's draw gauge or absolute? Gauge, very good. And I have to multiply by the area of the nozzle at station 1. So from that, you have done this several times in the homework, so I'll just write out the equation and ask if you have any question, and I can clarify it. Floor is open for question. Do you see the sign? Y is F minus. Y is the right-hand side as shown being positive. Y is the pressure gauge times the area positive. Do you agree with all that? Okay? So I'm after the force, so with some algebra, I have at the end further simplification. This resulting equation. Do you agree? Which is what you have done for the homework. Questions? Yes?
Why is it that in this problem, there isn't a pressure for 1, 2, or section 2.
Okay, so question is, what is the pressure upon 2, right? Do I get it? So first and foremost, when I say a free jet, what does that mean? Same problem as this. Free jet, what does that mean that the pressure at the nozzle exit? What is it equal to when I say free jet by default? Atmospheric, 14.7. Do you get that? So anytime the pump say you have a nozzle, the flow coming out is a free jet. Or even if I'm saying is that nozzle with the water or air exiting into the ambient is always a free jet. By that, the pressure is always 14.7. So if that is the case, what is the pressure net after accounting for the pressure due to atmospheric on the left side? What is the net pressure on the right side of the control wall? 0. Do you get it? That's very important. If you don't get it now, when you go to 2D, there's no, absolutely no. Okay? All on the same page? So someone come along, and she's going to argue, I don't like x to the positive to the right. I'd like to have x positive to the left. I leave the force and anchor the same assumption. Same pressure force. Same pressure force, nothing changed, except I changed one thing. I reversed the positive x direction. You think the answer is going to change? Let's find out. Let's find out. What is the sign for F now? Positive. Very important. That's why I cannot grade your test until you show me your coordinate. Because the sign is all that matters. Okay? So now it becomes positive. What about this term? Become negative. Now fill in the term in the bracket. Before you do that, let me ask you this. Does the m dot change? Now I reverse the plus 6 direction. Should I flip the sign for m dot? Mass flow rate, rho VA? Are you sure there's a V in the rho VA? Are you sure? I'm teasing you. No, this is no joke. You know. Do you want to flip the sign for m dot? Very good. No, it's a scalar. It's just rho VA. No direction. So fill in the missing term. What should that be in the bracket? Station 2. Station 2. Station 2. No? You are in doubt? You are not sure. All I did is to change this. U2. You are not sure. Okay, I need to slow down then. You don't see that as negative U2. You don't agree? You don't. How should I convince you? Do you see that should be minus? Because velocity is a vector. Just the magnitude U2 is not enough. Now it's U2, which is falling to the right. It happens to be exactly